The Ben Heck Show is brought to you by Element 14, the electronic design community and online store built for engineers and hobbyists alike. Join now and browse the store at element14.com.
So, what do you want to build this week?
I don't know. I mean, we made that Specky project. It was so cool, but ever since it's been done, there's been a hole inside of me the size of an 8-bit retro computer.
That sounds unpleasant.
I just don't know what would compare.
Amazing builds, exclusive mods, cutting-edge ideas, electronics, engineering, and more. Every week on Element 14's The Ben Heck Show.
Over the next few episodes, we're going to build a replica of the Apple I computer. Now, the Apple I was obviously Apple's first computer that was built back in the 1970s by Steve Jobs and Steve Wozniak in a garage, and it was sold as a kit. But like most computers back then, it was basically all off-the-shelf components, which means it's still easy to replicate today. So here are the basic parts that we're going to build in order to reproduce this computer. We're going to make a 6502 CPU-based single-board computer, which will have the CPU, the RAM, and the ROM. And that will execute by itself, but obviously you won't be able to see it doing anything. We'll have to test it with an oscilloscope. Then we'll build a PIA, peripheral interface adapter board, which will allow the 6502 to talk to things like an LCD or a keyboard. Basically, this old Apple I was just a terminal. You know, you just sent characters into it and it spit characters out. That's what this will do. And I think it might be fun to envision what if the Steves could have made a proper case for it back in 1975. What would it have looked like, you know, vintage 1970s, and try to make it fit that aesthetic. So let's get started by making the single board 6502 computer. I'm going to start by adding sockets for the ROM, RAM, and CPU onto a PCB. It's good practice to wire the power connections before wiring the data connections, so I'm going to attach power and ground. The power rail goes along the top and the ground rail goes along the bottom. This matches up to the power and ground on most chips. Now let's get the data bus wired. I have to do this in a certain sequence to make it easier to solder. I wired the 8-bit data bus going from the RAM to the ROM to be as flat as possible. Now I'll connect them to the CPU. I'm wiring the address bus in whatever sequence keeps the wires laying as flat as possible so they're easier to wrangle. I'll finish up the last few wires in the RAM and connect it to the EEPROM here. They should all nest together nicely and then travel out to the CPU. I'm keeping the wire contiguous wherever I can so I don't have to solder ends together. What I do is strip off a little insulation, but I don't cut the wire so I can still attach it in series and make everything easier. I just use my fingernail to pull the insulation off. Here is the completed address and data bus for the ROM and the RAM. They go over to this side and then they'll attach to the CPU. This bundle of wires that comes down here are for the chip select. That is, when the system has to decide if it's talking to the RAM or the ROM. We'll attach those a bit later. Some of the CPU pins, even though we're not using them, still need to be pulled up to a positive voltage. We have a positive voltage rail here, and that's where I'll attach the resistors that will pull up these pins. We'll do that first so we have room for other wires later on. We wire stuff at the bottom first, and then layer other connections on top of it. Hello. We're also going to need to connect wires to anything else we need before we lay down the address wires over this area, because we don't want to melt the wires that are sitting between other wires. It's all about doing things in the right order. It's time to attach the address and data lines from the RAM and ROM to the CPU. Some of these extra wires I've added, we might not need them, but at least I've got the wires attached ahead of time in case we do. It's easier than going back and trying to add it in later. I'm trying to do this as neat as possible, which makes it easier to debug, easier to fix, and also just works better. The address lines and the data bus have all been connected between the RAM, ROM, and CPU. Now we need to add some additional circuitry to select between the ROM and the RAM during the program execution. Let's go to the whiteboard for an explanation of how memory addressing works. The basic system consists of a 6502 CPU, RAM, and ROM. Originally, the Apple I came with 4K of RAM. Obviously, RAM is infinitesimally cheaper now, so we're going to put 32K of RAM in along with a 32K EEPROM. Now it doesn't need all the 32K EEPROM, which is why we have to divide it up. So here's basically how it works. A 6502, or basically pretty much all of the old 8-bit CPUs, could access 64K of memory, which is technically 65535 bytes. There's 16 address lines labeled A0 through A15, and those address lines let you select which byte in memory you're looking at. The last bit of the address line, A15, is pretty useful because that's what selects between the first 32K and the second 32K, or you call them bank 0 and bank 1. Bank 0 will be entirely RAM, so that's good. And then bank 2 will be ROM as well as a few other things. So using our logic circuitry, I think we'll do it with like a NAND gate and a NOR gate. We can select between, this bank and this bank, and then if we're in this bank, so if A15 is high, we also have to do some sub-selections based off if you're trying to access this portion of memory for the cassette code, this portion, which actually, it shouldn't be selecting the ROM, it should actually be selecting a separate peripheral. So it's like, if it goes to this portion of the ROM, it should actually disable the ROM. And then the basic, which is the basic interpreter, we'll store that in the EEPROM, so you don't have to type it in or load it from a cassette. And at the very top of the EEPROM is the WAS monitor, which is what the system executes when it boots up. So we're going to build our EEPROM image to look like this 32K image, making sure the specific bits of code are in the right places. Now it's time for a tech timeout. Some fun facts about the origins of Apple. The Apple I originally sold for $666 in 1976, which would be $2,900 now. Can you imagine a computer kit that cost that much? It was a different era. Steve Jobs used to work at Atari before he founded Apple, and he made the arcade game Breakout, the walls and the blocks. And the third fun fact, Steve Wozniak hand-assembled his WAS monitor to run the Apple I. He didn't have a compiler, he actually just wrote everything out in machine language. Insane. We've put together a 6502 computer with ROM, RAM, and addressing chips. To test it, we need a ROM of some sort. This drawing here shows the memory map of the Apple I computer. I got this from one of the Apple clone pages. We have basically RAM in the first 32K of memory, and then the second 32K of memory, which is where we're going to put our ROM, is where we have the cassette interface, BASIC, the Crusader, which is an assembler, and the WAS monitor, which is what you get when you turn on the system. So these are things we actually need to have in ROM. Our ROM is going to be a 32K ROM, but the memory is mapped to a 64K space. What we need to do is take these values and then subtract 8000 hex from them. So instead of being at the top of memory, they're at the bottom of memory in a 32K space. So if something, for instance, needs to be at C000 in the memory map, that means on ours, if you look at it here, I'm assembling it in a text editor, we start at 4100 hex. And then if BASIC starts at E000, that actually starts at 6000. So let me just show you, if I get a calculator here, in hex. So we go, let's go to hex mode. Why can't I just say go to hex mode? I mean, our computer should be able to do that. So for example, if BASIC is supposed to be addressed at E000, we need to put it into our ROM at a different position. So we subtract 8000, that gives us 6000. So in our 32K ROM that sits at the top of memory, BASIC will start at 6000, and it does. So we have to make sure this all lines up. Looks like it does. Down here at the very bottom, this is the reset vector. This is what the 6502 vectors to when it's reset. Reset vector. It doesn't execute code at the reset vector. Rather, the reset vector tells it where to start executing code. So when the 6502 turns on, it looks at this here, which is a little endian. So it's actually FF00. and then the processor jumps to that location and starts executing code. So FF00 in the memory map would be right here, that D858A0. That is the beginning of the WAS monitor. Looks like this ROM is put together correctly. So I basically took the cassette interface, BASIC, the assembler, WAS monitor, and put them all in the correct positions in a hex file. Now I'm gonna burn that using my Petronix BX40 that I got from Element 14. And then we'll have a ROM that hopefully will drive our system. I did a little more work to the Apple One board. I added a bus header here and a 1 megahertz oscillator. An oscillator is different from a crystal in that if you provide 5 volts and ground to an oscillator, it'll just spit out a square wave. You don't need any additional circuitry. So it works pretty good. I had this one laying around. The square wave oscillator drives the CPU, and the CPU will read from the ROM and RAM, and then we have a few chips here to do the address decoding. There's a 3 to 8 digital encoder. Then we have a NAND and a NOT, and that allows us to do all the address selecting that we should need. The idea here is the AV circuit and the keyboard will plug into this, so we're building a 6502 single board running the WAS code here, and then we'll attach the AV onto it. Before we go much further, we need to see if it works. So I'm going to hook it up to my bench power supply, give it 5 volts. Then I'm going to hook it up to my oscilloscope to look at the data bus. Do need a few other things here. We need a clean reset. When you turn the system on, it's going to be in a weird state, so you want to actually reset it after you turn it on. We can put a timer circuit in to do that later, but for now I'm just going to use a button. So this button is going to attach, oh, that's incorrect. It's going to attach here. These are logic probes. They come in a bundle like this, and there's 16 of them total. And we can use these to read digital data. Now, digital data is different from a regular oscilloscope input, as it's just looking for zeros and ones, highs and lows. And the thing that's cool is that it'll actually show us the hex values if we tell it to. And there's a good reason for that, which you'll see in a minute. So first we need to make sure the grounds are connected. Always got to have ground. Now there's an 8-bit data bus and a 16-bit address bus on the 6502. What we're going to look at is the data bus. That will be enough information to tell us if this is working. So we're going to hook up the LSB of the data bus, D0, and then move up from there. Gonna need a montage. Anything where you need to go. Just a beginner to a pro, you need a montage. Montage, even Rocky had a montage. Rocky was nothing but a montage. Well, the sequels at least. The logic probe plugs in here into the Tektronix scope. Cool. Now we don't see anything yet because we haven't enabled it. So I'm gonna push this. Okay, now it's active. Now we want to make sure that we set certain things on it. Let's see, so, all right, let's take a look here. Let's make sure turn everything on for starters. Okay, so here's all 16 data lines. We want to look at data lines 0 through 7. There's 8 of them. We also want to look at A15. On the address line, A15 triggers the first or second 32K bank of EEPROM. And the reason we want to look at that is because of the reset vector. The 6502 will go to pretty much the top of its address space and look for an address to begin execution at. So when the CPU is looking at the top of the address space, that'll trigger A15 to be high. We can use that as a trigger point to see when the cycles have started. We can do that in just a second. All right, so let's turn off D15 to D8. Okay, now I'm gonna manually add D8. I'm using D8 as the A15 line. Yeah, that doesn't sound correct, but it'll look better on the screen because if we hook up, watch this. Maybe there's a way to, not do this, but if we add D15, it appears way up there. So I'm just gonna use D8 as a trigger. Okay, all right, we got that. All right, so that's where our address is going to show up. So now we want to do something, we want to set a trigger point. So we're going to go into the oscilloscope and hit menu. And we want an edge trigger. Slope, rising edge, so that's going to be that one right there, which means going to a 1. Source, we're going to select D8. So the oscilloscope is just going to sit there doing nothing until it sees a rising edge on D8, which means, oh, the 6502 is trying to read its ROM. Read its ROM. Okay, let's set the level here. Let's go to 5 volt CMOS, old school. Yeah, all right, that's your voltage level. That's the level, that's the difference between a 0 and a 1. So this is the active data coming off of the processor, and we're seeing the data lines as well as the ROM select, which is this indicator right here. I've got it on line 8. So that's actually an address line. In order to capture data, we're going to use the trigger function, which is something most oscilloscopes have. All right, so source is going to be D8. Wait, I guess we already explained this, didn't we? All right, so now we're going to see if we can capture this. In the oscilloscope, I'm going to go from run stop. So you can use run stop to stop the data and look at it, but it's manual, you're just pushing a button. When you go to single, that's where you can hit it with the trigger. I'm holding down reset to keep the processor off. The trigger's enabled. I hit single instead of run stop. I'm going to release reset, and it captured the beginning of the 6502's cycle. But what does it mean? Let's take a closer look. We can turn on the bus here, and we see that it's a parallel bus, and it's labeled as such, and the bus display is the bus and the hexadecimal, so that's all good. Let's zoom in a little bit. Okay. All right, so earlier you remember I was making a ROM, and here we can see what's going on. See this, 00FF, that's the CPU loading the reset vector. Let's compare it to the hex listing. D8, 58, A0, 7F, 8C, 12, D0, something else happened, A9, A7, 8D, 11, D0, something else happened, 8D, 13, D0, 00, C9, DF, F0, 13, C9, 9B, F0, 03, C8, 10, 0F, A9, DC, and then this 20 here, that's a jump subroutine, so then it's going to go to a completely different part of the code. Let's see if we can figure out where that went. Okay, wherever it went, it looks like, okay, 12, 0. Oh, okay, so it looks like it jumped down to, jump from here down to there. C12, D0. It's probably going to be a 6-0 after it's someplace, or not. Well, the moral of the story is it looks like the 6502 is working. So using the oscilloscope, we were able to make sure that our circuit was working before we hooked any other components up to it. So we didn't need a keyboard, we didn't need a display. We were able to test it using the oscilloscope. And it's really nice, this Tektronix has the, it can show the hex. And it can also show it in binary. So if I want to look for this, load the accumulator with this binary value. Let's see, let's just look for it. That's going to be pretty early on the code. I'm going to go to the bus, and I'm going to turn the bus display into binary. Okay, now we're just going to look for that. We need to zoom in a little bit more because binary takes a little bit more room on these. Load accumulator, and then that binary value 10100111. There it is. So yeah, it looks like everything's working. That's all the time we have for today. In our next episode, we're going to attach some more circuitry to this so we can use a keyboard and a display to see what's going on and put in some data. We'll see you then. I wired the 8-bit data bus going from the RAM to the ROM to be as flat as possible. Now I'll connect them to the CPU. That's why it's called a bus. It's connected to everything. Kind of like how a bus drives around and is connected to all the streets. I guess it just rolls over the streets. Although in some places the buses are electric, in which case they're connected to electricity wires. So they're easier to wrangle. Wranglers, your favorite genes. Just when you thought they couldn't be more boring on the Ben Heck Show, we do this. Of course, I mean, why would it work? Why would we want it to work? In today's dollars, that would be more. Sorry, I hate the calculation. and nothing can fill it, not even pi. Also, the size of that hole displaces many vital organs. I don't even know if I'm still alive, actually.
Wow, you're kind of like a freak of nature, a mystery of science.
I had to do 2 takes.
Okay, fine.
The Ben Heck Show is brought to you by Element 14, the electronic design community and online store built for engineers and hobbyists alike. Join now and browse the store at element14.com.